We're continuing with the back page of AP Exam Review Worksheet 3. Look at number 5 here. If y is equal to 1 plus x squared, quantity raised to the x power, then dy dx equals. So anytime we have an expression that involves a variable raised to another variable, the only way that we don't have a rule that will, a derivative rule that will take care of this particular instance. So we have to resort to something called log differentiation. So the idea behind log differentiation is that if we can find a way to bring this exponent variable x down out of the exponent form, then we can apply rules that are a lot more easily available for us to apply. So what we can do is we can introduce logs into the equation, and then we can use log properties to bring the exponent down. So first thing we're going to do then is we're going to introduce logs into the problem to allow us to move this exponent variable x. So we'll do natural log of y is equal to natural log of 1 plus x squared quantity raised to the x. Okay, we can bring this x down in front, and now we can apply the appropriate rule on both sides of the equation. So the left side, natural log of y, looks like now we have to involve implicit differentiation, because now the equation is not nicely separated with y by itself. So now the derivative for natural log of y is u prime over u, right? So the derivative for y is 1, so 1 over y, and then we have to attach dy dx. We're involving y's derivative. On this side here, notice that x and natural log of 1 plus x squared are two separate terms. So because they are related to one another by multiplication, we have to go through product rule. So f prime g plus f g prime. So f prime, x's derivative is 1 times natural log of 1 plus x squared plus the original function here times the second function's derivative, so u prime over u. 1 plus x squared becomes 2x over 1 plus x squared. Multiply this through, and the last step now is to isolate dy dx. So we'll multiply y on both sides and move the y over to the right side. And now we want to get y in terms of x. So replace y with the original equation in terms of x. So that should be able to help match one of the answer choices, 1 plus x squared raised to the x times natural log 1 plus x squared plus 2x squared over 1 plus x squared. So answer choice A. Okay, number 6, if x squared plus y squared equals 25, what's the value of d2y over dx2 at the point 43? So this is asking for the second derivative at a particular point. So we have to maybe go through implicit differentiation twice. So let's go through this process here. All right, so implicit differentiation, because we don't have y nicely separated on one side of the equation. So we're going to find the derivative of each term, and then whenever we come across y's derivative, we have to make sure we attach and include dy dx. All right, so x squared becomes 2x. Y squared becomes 2y. We attach dy dx. 25 is a constant, goes to 0. Now let's solve for dy dx. So dy dx is subtract 2x divided by 2y. So negative 2x over 2y, or negative x over y. So we're halfway there. We've reached first derivative, but we still need to get down to the second derivative. So now to find the second derivative, which is d2y over dx2, looks like these variables are related to one another by division or quotient of each other. So we go through quotient rule for derivatives. So f prime g minus f g prime all over g squared. So f prime, so negative x becomes negative 1. Y stays minus the original numerator, negative x, times the derivative of the denominator. So y's derivative becomes dy dx, or 1 times dy dx, all over denominator squared. Don't forget that, y squared. So if we clean this up a little bit, we get negative y plus x times dy dx, and then we want to eventually convert our second derivative to be in terms of x and y. So if we look at dy dx, we have a nice substitution for dy dx, because dy dx we found at the end of the first derivative, dy dx is negative x over y. So negative x over y replaces dy dx. If I multiply the numerator through, I get negative y minus x squared over y all over y cubed over y squared. Now, we don't have to actually continue simplifying because we're not asking to find the second derivative function. We're asked to find what is the value of the second derivative. So once we've arrived at the second derivative, we can just plug in our ordered pair because all we want is a numeric value out of this. Now, if we're trying to find the second derivative, then we'll have to multiply this through and try to clean up this complex fraction. But we can go ahead and skip that step and jump directly into plugging in our ordered pair. So 4 plugs in for x, 3 plugs in for y. So negative 3 plus 4 times 4 over 3 all over 3 squared. And if we clean this up, we get negative 3 plus 16 over 3, which is 7 over 3 all over 9, which is 7 over 27. All right, number 7 here. Consider the curve given by x squared plus 4y squared is equal to 7 plus 3xy. Part A, show that dy dx equals 3y minus 2x all over 8y minus 3x. So again, we want to find the derivative, but again, notice the equations, the variables are mixed with one another, so we have to go through implicit. Not only implicit, but notice you have 3x and y here. We have to also go through a product rule. Okay, so we can treat 3x like the first term and y as the second term. Okay, so let's step through these steps here. All right, x squared becomes 2x. 4y squared becomes 8y dy dx. Okay, equals 7's a constant, goes to 0. 3xy, now I have to go through product rule here. So f prime g plus f g prime. I'll treat f like the 3x and y as the g function. So f prime, 3x becomes 3 times the original y function plus the original f function, 3x, times y's derivative, which is 1 times dy dx. All right, so now it's just a matter of trying to get dy dx by itself. So algebraically, we're going to move some terms around. We're going to put the terms with dy dx on the same side of the equation. We can move all the non-dy dx terms on the other side of the equation. So once we're here, we can factor out the dy dx. Parentheses is 8y minus 3x. So now to isolate the dy dx, we can divide the 8y minus 3x over to the right side. And now we have 3y minus 2x equals 3y over 8y minus 3x, which matches what part A is asking us to show. Okay, part B, show that there is a point P with x coordinate 3 at which the line tangent to the curve is horizontal. So when x is 3, we're trying to show line tangent to the curve is horizontal. So if we think about what that means, horizontal tangent means once we have dy dx spelled out, the numerator, whatever the numerator of the dy dx is equal to 0, that will be where horizontal tangent is going to occur. And then just as a reminder, vertical tangent is going to occur when the denominator of the derivative is equal to 0. Okay, so x coordinate of 3. Okay, so what we can do is we can set the numerator equal to 0. So here's the numerator of the derivative, 3y minus 2x. We set that equal to 0. They tell us that x is 3. Okay, x coordinate is 3. So if we plug 3 in for x, we get 3y minus minus 6, or 3y equals 6. And if we solve for y equals 2. So for part B, we know that when y is 2, that will cause the numerator of the derivative to be equal to 0, and so therefore it's going to be the location where the slope of the tangent line is going to be horizontal, okay, or 0. Part C, find the value of d2y over dx2, which is the second derivative in part B, found in part B. Does the curve have a local maximum, minimum, or neither at point P? Justify your answer. So we need to first find the second derivative, working from the result from part A. So to find the second derivative, we have to go through quotient rule here and implicit differentiation, because we have y's again mixed with the x's. So we have go through quotient rule here. F prime g minus f g prime all over g squared. So f prime, 3y's derivative becomes 3 dy dx. 2x becomes 2. This is the f prime times the g function, okay, minus the f function, 3y minus 2x all over the g prime. So 8y becomes 8 dy dx, 3x becomes 3, all over denominator squared, all over g squared. All right, so it says find the value at point P found in part B. So part B, the order pair is 3, 2. So we can just plug the order pair 3, 2 into this whole second derivative equation here. So we know dy dx at that moment in time is 0. So plug 0 in for all the dy dx's. Replace 3 in for all the x's, and 2 for all the y's. So once we do that, then the result will be 6 minus 6, which is 0, over 7, which is 0 over 7 is a real number. That's actually going to be 0. Okay. So does the curve have a local maximum, a local minimum, or neither at point P? So what we can do here is I'm sorry, what I just, when I went from here to here, this was actually the result of the first derivative. Sorry, I should have plugged all this into the result here. So if we plug all this in, sorry, 0 in for all dy dx's, x gets replaced with 3, and y gets replaced with 2. So sorry, all the result is down here. And if we work all this through, it's a little messy here. If we work all this through, we'll get negative 14 over 49, or negative 2/7. So that is the result. That's the answer for the value of d2y over dx2. And we know that since the second derivative is negative and the first derivative is 0, then this fulfills the condition for the second derivative test, which tells us that if a point has a slope of 0 and is also produces a value that is concave down, then the graph must have a relative max. Okay, so just as a visual here, if at a point the slope is 0 and it's part of a concave down graph, then we know that at that point there must be a relative max at point P. So these conditions are part of ones for the second derivative test.